Okay, so we will talk now about refraction. So in the first slide in the lecture, we said the behavior of light as it passes through interface. So we said that some light will be absorbed, some light will be reflected, and some light will be refracted. So refraction means passage of light from one medium to another medium. So here, if we can see this spoon, you can see it is bended. So is it actually bended? No, because this is just your eyes can see that the spoon is bended because light rays passing through the spoon from here and from here will pass through different refractive medium. So here is air and here is water. So as you can see, a parallel line or a straight line, you will see it bended because it passed into two different media. This is what is meant by refraction. So it is the bending of light as it passed between two different media. So this is a nice photo that show both reflection and refraction. So you can see here this calendar. You can see through this lens, and you can see that there will be bend of the image. So the image here like a change in size and the change in direction. So this in this part of the glasses, the image has undergone the refraction. However, in this part, you can see there is a reflection from the window. So the reflection occurs here at this surface from the glasses. So you can see that refraction and reflection occur at the same part, but it is just the angle at which the light enter this medium, and this will control whether it will be reflected or refracted. So, scientifically speaking, refraction is the change in direction of light when it is passing from one transparent medium to another of different optical density. So, if we have a light ray like this incident ray passing from air to glass, there will be some light rays that will be reflected, and this will be the law of reflection, in which the angle of incidence will be equal to angle of reflection. However, there will be some light rays that will be refracted. So this refracted light ray will refracted to pass into the glass. So the light ray will not pass into the same direction, but it will bend. And this bending will form an angle with the normal that is called the angle of refraction. And this bending occurs because this light passing from a medium of optical density or a refractive index to another medium of different refractive index or different optical density. So the question is, what is the optical density, or what is the refractive index? Optical density is the property of offering resistance to light, leading to decreased speed. So this this you can see here, this should be in a vertical line, but however you can see that it is refracted, so it will show bending, and this bending occur because this bluish water can cause a slowing of the light rays passing from it, leading to this displacement. And also in this spoon, you can see that the spoon is passing in the air, then it passes into the glass, then it will pass into the water. Different medium or different media will offer different resistance to the light or the parallel light or the straight light, so it will lead to bending of the image, as we can see here. This property of offering resistance will cause more refraction. So the more dense the optical medium is, the more refraction, as it will cause more decrease of the speed. So as you can see here, this man is lying inside this box or this glass top filled of and I don't believe that this is a normal water, but it is like any material that is have a high refractive index that will lead to a large displacement and large bending of his head and his arm. So you can see that this is a frank example of refraction. So why the refraction occurs? As I told you that the refraction occurs due to change in the speed of light. So just imagine that this team is moving, or A and B and C and D and E. These girls are passing through with the same speed, and then the girl D and the girl E pass into some rough surface. So these girls will slow down, and the A and B and C will continue on their speed. So there will be bend of this wave of girls, leading to refraction. So this is exactly what happens with the light. So the light, it will undergoes a different or will pass through different refractive media. This refractive media will offer different resistance to light. So the least resistance will cause more rapid passage of light, while the highest resistance will cause bending and slowing down of the light, leading to its bending. Again, it is the same thing when you move with your car into a paved road. So you will move with your speed, then and suddenly you will enter into a muddy surface. So when you enter the muddy surface, this wheel will slow down while this wheel will continue on its speed. So if this wheel continue on its speed as it is moving from the paved surface, this will lead to movement of the car like this. However, slowing down of this wheel on the muddy surface will lead to a bend of the car toward the normal, or toward the vertical, the principal axis. So this will lead to change of the direction of the car, leading to bending of the pathway. So what are the factors that affect refraction? We need to know when we are studying the optics, the factors that affect everything. So as we said in the physical optics, the factors affecting diffraction, for example, as we will go through the optics, you will always find that there are factors that govern everything in optics. Should be studied well, because these are areas of exam, or areas that's asked in the exam. So what are the factors affecting refraction? It will be the refractive index, it will be the angle of incidence, and the wavelength of light. So the shorter wavelength of the light, so light toward the blue spectrum, will have higher energy and higher frequency, leading to more bend and more refraction. This will be in contrast to the lights of the longer wavelengths. So the light of longer wavelength, like red, this light will undergo a slower refraction, and more as they will have lowest energy or the lowest frequency. So angle of incidence is we have already discussed, and the refractive index, as we said, it will be the resistance that the material will offer to the light. So how can we calculate the refractive index? If we want to know the refractive index, we need to know that there are two types of refractive index. There is absolute refractive index and the relative refractive index. The absolute refractive index, meaning that the refractive power of this substance or this material in comparison to air. So the air here is a standard, as the speed of light in the air is equal 1. So the refractive index of the air is equal 1. So this will be our standard. And the refractive index of any material, so the refractive index is always can be referred to as n. So the speed of the refractive index of any material, or n of any material, is equal to the speed of light in the air divided by the speed of light in this medium. So this will be called the absolute refractive index. So if we want to know the refractive index of the glass, we divide 1 over the speed of light in the glass. So as I told you, it is just a property of offering resistance to passage of light that will affect the speed of light. While relative refractive index, meaning that it is the refractive power of substance in comparison to another substance. For example, if we wanted to know the relative refractive index of water in relation to glass, then we will divide the refractive index of the glass over the refractive index of water. So the ratio here will be the relative refractive index of water to the glass. So these are some examples of the refractive index. They are asked in the exam, so you should memorize these figures. So the refractive index of the air is 1. The water, including the aqueous, it will be about 1.33. The cornea will be 1.37. The crystalline lens will be 1.386 and 1.406, depending on whether it is cortex or whether it is the nucleus. There are two types of glass. There is the crown glass and the flint glass. The flint glass has higher refractive index. So if there is a glass is made of flint glass, it will be more compressed or more thin. And the diamond has a refractive index of 2.5. So we studied the angle of incidence and the angle of reflection. And what is the angle of refraction? So I think that you can guess what is the angle of refraction. So if we have here an incident light rays that will fall in interface between the air and water, and some of light rays will be reflected, forming an angle of reflection. So some of these light will be bent, leading to an angle between the refracted ray and the normal. So this angle is called the angle of refraction. So here again, the angle of incidence. When the light hit in the interface, it will refract, leading to bending of the light, and the angle between the refracted ray and the principal meridian or the normal is called the angle of refraction. So the behavior of the refracted light is different according to it is passing from more dense to less dense, or from less dense to more dense medium. Meaning that if the light is traveling from a less dense medium like air to a more dense medium like glass, then the light slow down. Since the light slow down, then the light will be bent more toward the normal. So again, when the light is passing from less dense to the more dense medium, the refracted ray will be passing or will be bent toward the normal. This will be the reverse if the light is passing from the more dense to less dense. So if the light is passing from the more dense, like the glass, as we can see here, this is the angle of incidence, and the light will be refracted. As it passes from the more dense to less dense, the light become more speedy, or the light become more fast. And since the light become more fast, it will be refracted away from the normal. So it will be bending away from the normal. So this rule is very important. Let's now come to another rule, which is called the Snell's law. The Snell's law will govern the angle of incidence and angle of refraction, and also will take into consideration the refractive index of both media. Meaning that there is an angle that will between the angles of incidence and refraction and the refractive index of both medium. We don't need to know how do they calculate this because this is not our business, or this is not our concern, but we need just to know what is the rule and what are the applications. So Snell's law applies to refraction of light in any situation regardless of the medium. So for example, if we have here a medium, this medium is having a refractive index called N1, and the light ray fall from the medium, or the incident light ray fall from the medium number 1 into the interface. So this will be the angle of incidence. Then the light will be refracted. So it will pass into the second medium, which has a refractive index of N2, and the angle of refraction will be called the R, or angle of refraction between the refracted ray and the normal. So the angle, or the rule here is that the refractive index of the first medium multiplied by sine of angle of incidence equals the refractive index of the second medium multiplied by sine of the angle of refraction. So this is called the Snell's law. So what happens if we have one of these medium is air? So if we have the N1 as air, can we know the angle or the refractive index of the second medium? So let's have this equation. If the N1 is air, so the refractive index of the N1 is 1. So the N2 will be equal the sine of angle of incidence divided by sine of angle of refraction. So this is just a simple math. I hope that you are good at math, because you will need this skill much in optics. So N2 will be equal sine I over the sine R, or sine N2 equals sine I divided by the sine R, which is sine of the angle of incidence divided by sine of angle of refraction. If we have refraction through the parallel plate of glass like this, so this is a glass and has a surface, one surface, and another parallel surface, so what will be the behavior of light passing through this parallel plate of glass? This is the incident light ray passing from the air to the glass, so it will pass from the less dense to more dense. That's why the light ray will bend toward the normal as it slows down. Then when the light is passing from the glass to emerge to outside the air, then the light ray will be emerging outside or away from the normal, as it will pass from less dense to the more from more dense to less dense, leading to refraction away from the normal. Then if you now complete this light ray, you will find that this light ray will be parallel to the incident ray will be parallel to the emergent ray. It is just laterally displaced. So by light passing obliquely through a plate of glass, it is deviated laterally. So the emergent light ray is parallel to the incident ray, and the direction of light is unchanged, but it is just laterally displaced. Let's now come to the fun part, which is the clinical application. So why do we study this? So what are the applications of refraction? If we have an object that's placed in the water like this fish, actually we don't see it in its actual location, or we do not see it in the real position, but we see its image. And this image, because of refraction, as I told you before, this is the fish, this is the hunter, or this is the fishman, wanted to catch this fish, and since it is present here, our eyes cannot see broken lines, so our eyes can see only straight lines. So we don't see this fish in the real position, but this fish will emerge light rays that will pass into the eye, and we will only see the extension of the light rays, so we can see a virtual image of this fish, which looks closer to the water, and this will lead to a false localization of this fish. So objects immersed in water looks closer than they really are. The second important clinical application, which is the critical angle. So what is the critical angle? If we have here a more dense material or more dense medium like water, and this is the less dense medium, which is air, and we have a light that is passing from the more dense to less dense. So what will happen? As we know from refraction, it will be refracted away from normal as the light speed up. So what happens if we increase the angle of incidence? As we say that the refraction will depend on different factors like refractive index, like the angle of incidence, like the wavelength of light. So here we are fixing the refractive index of both materials, and we are fixing the wavelength of light, only we are changing the angle of incidence. So when we are increasing the angle of incidence, the angle of refraction will increase, and again increasing the angle of incidence, and the angle of refraction will increase until they become parallel to the surface. So they become perpendicular to the normal and become parallel to the surface. So the light is not emerged from or not refracted outside the water, or not refracted outside the more dense medium. So what happens if we increase the angle of incidence furthermore? This will lead to reflection of the light. So this reflection occurs when the angle of incidence increase up to a limit. It is called the critical angle. So if we increase the angle of incidence to a limit that is called the critical angle, this will lead to total reflection, or the angle above, or any reflection, or any incident angle above this angle of critical angle. This will lead to total internal reflection of light rays. So it will be no refraction, but will be reflection. So what is critical angle? It is the angle of incidence of light ray passing from the dense medium to a less dense medium. This is important, and this will be the rule, at which emergent light rays will be a rise 90 degrees to the normal. So this will be the angle of or critical angle, the angle of the instance at which the angle of refraction will be 90 degrees. Above this angle, total internal reflection will occur. Let's back to Snell's. So Snell's law, as we just mentioned, we all know it. So let's have an application in which we will use the critical angle. So we have here the N, or the refractive material, or the refractive index of any material, and we have here the N dash, which is the refractive index of the air. So we will call it N dash. And we have this, as we all know, the refractive index of the air will be 1, and this will be the lowest refractive index of any material. So this material, or the N, is more dense than the air. So if we have an instant light that will pass from N toward the air, and then the angle will be between the instant light ray and the normal, it's called angle of incidence, or I. Then if this angle of incidence is the critical angle, then the light ray, or the refracted light ray, will pass parallel or toward the surface. So as the angle of R will be 90 degrees. So the angle between the refracted ray and the normal will be 90 degrees, and it will be called R, or angle of refraction. So we know from the Snell's law that N multiplied by sine I equals N dash multiplied by sine R. So we have some information, or we have some data input that we know already. So N multiplied by sine of the angle of incidence equals N dash, which is 1 of the air, and sine 90 degrees, which equals 1. So sine 90 equals 1. So again, N, or the refractive index of the more dense material, multiplied by sine I equals 1 multiplied by 1. So it equals 1. So if we have now moved the N to the other side, it will be in the denominator. So sine I, or the critical angle, will be equal 1 divided by the refractive index. So to know the critical angle of any material, we need to know what is its refractive index. If we have this information, if we have the refractive index of any material, we can know what will be the critical angle of it. Let's have some clinical applications of critical angle and total internal reflection. There are some prisms that we will discuss in the second lecture, and we will know know their applications in the instruments. So we will just know the basis of them now, and we will know their uses later on in the instruments. So there is what's called reflecting prisms that use the principle of total internal reflection. So one of them is called the right-angled prism. So we have here the right-angled prism. It is right-angled, so it has 90 degrees angle, and the other two angles will be equal, 45. If a light ray strike the angle, or strike the surface that is adjacent to the 90 degrees, and making an angle of 45 degrees with the normal, then this light will undergo total internal reflection. So it will not refract from the other side, but it will be reflected to the arise from the other surface of the adjacent surface. So it will hit one surface adjacent to the 90-degree angle, and it will change, or what will reflect from the other surface adjacent to the 90-degree angle. So what is the characters of images? The image will be deviated 90 degrees, as you can see here. So this is the 90 degrees, and you can see that the image here is deviated to 90 degrees. So if we have a device that we want to deviate the image 90 degrees, we use the right-angled prism. Also, the image is laterally transposed. So you can see here that the mic is on the left hand, now it is becoming on the right hand, so the image is laterally transposed. So this is the right-angled prism. What about the other prism, which is called the poroprism? In the poroprism, the light rays will strike the surface opposite to the angle, or opposite the right angle. So when the light rays strike the surface at the adjacent, strike the opposite surface opposite the 90 degrees, it will undergo first internal reflection, then another total internal reflection, then it will emerge from the same side. So it will enter the wall adjacent, or enter the surface opposite to the 90 degrees, and it will emerge from the same surface opposite to the 90 degrees angle. So what will be the character of the image? As you can see here, the image will be 90 degrees deviated. So it is deviated like a half a circle. So if we have, this is the image, or this is the object, and this will be the image. It will be deviated 180 degrees. It is inverted, like, see, you can see it is upside down, and again it is laterally transposed. So it is inverted and laterally transposed. Finally, the third type of the reflecting prisms is the dove prism. In the dove prism, the image is not deviated. So it enters from the one surface and it arises from the other surface, or the light rays is not reflected or not coming from any or doesn't suffer any deviation. So it is just inverted and just laterally transposed. So if we have here an image, then this image will become inverted and laterally transposed. So this will be the characters of image of dove prism. So to summarize, we have the right-angled prism. The right-angled prism will make the image deviated 90 degrees, as you can see here, and become laterally transposed. But it is erect, as you can see. The poroprism will form an image that is deviated 180 degrees, like this F, and it is inverted, so it is upside down, and it is laterally transposed. The dove prism doesn't cause any deviation of the image, but it is just making it inverted and laterally transposed. Prisms are used in almost in all optical instruments. So like here for this example, in the binoculars, these binoculars, you can see that the light rays enter from the objective piece, then it will pass through this poroprism, then it undergoes total internal reflection, then it will enter this poroprism and undergo total internal reflection in order to reach the eyepiece. And this is another example of the right-angled prism that will cause the image to arise from the other side. So these are usually used to change the direction of light. So if we, and also in the slit lamp and other devices, they are used to change the way that the light moves. Other application of the total internal reflection and the critical angle is the Gonyo lens. So the Gonyo lens is a lens that is used to examine the anterior chamber. So what happens if we decided to examine the anterior chamber using the slit lamp? We will see nothing, because light rays reflected from the angle of the anterior chamber will hit the surface of the cornea, and as it goes from a material of higher optical density, which is the cornea, to a material of or medium of less optical density like air, they will undergo total internal reflection. So we will not be able to examine the angular structures. So to overcome this problem, we use a lens that's called Gonyo lens. This Gonyo lens has optical density or refractive index that is more than the cornea. So when the light is hitting the cornea from the angle, instead of having total internal reflection inside the eye, they will pass through a material of less dense to a material which is more dense. This will lead to refraction of this light rays, and then it undergoes reflection from a mirror here. This mirror for examination of the angle, or there are other mirrors for examination of the retina. Then from this mirror, light will be reflected to the examiner's eye. So this is another example for the total internal reflection. Other example for the critical angle and total internal reflection is the fiber optic. So how do the fiber optics work? So fiber optics can transmit light, and this light can bend toward this fiber optics. So we can be coiled, and the light can still pass through it, and we can illuminate different structures using the fiber optic. So this can be done by the principle of total internal reflection and the critical angle. So this can be done if we have this fiber optic has a core of transparent material that have higher refractive index. So the lumen of the fiber optic is not empty. It is made of a material that has a higher refractive index, while the cuff or the wall of this fiber optic is made of a material of lower refractive index. So when the fiber optics or the light passing through the fiber optic, it will undergo a series of total internal reflection until it reaches the examiner's eye. So the light here will undergo total internal reflection as it will pass from the material of higher refractive index to material of lower refractive index until the light will be coming out from the pipe. So there are different uses for the fiber optics in not only in ophthalmology but in medicine as all, like bronchoscopy and arthroscopy and colonoscopy. So these fiber optics can pass through different structures, can bend, and the examiner can see through the light from it, but because there is a principle of total internal reflection. Another application of the critical angle is the sclerotic scatter. So sclerotic scatter is a technique of examination in a slit lamp that is used to visualize the subtle corneal opacities. So this can be done by illuminating the limbus, like here, by projecting the light into the limbus, and then the light will undergo series of total internal reflection in the cornea, like this. So we illuminate the limbus by an angle that is more than the critical angle, so the light will undergo a series of total internal reflection inside the cornea until it emerges from the limbus of the other side. As you can see this halo. This halo is formed by emerging of the light from the other side of the limbus. So what is the value of this technique? This is used for illumination of subtle corneal opacities. So there are maybe some corneal opacities that are very faint, and they can't be visualized by normal techniques, so we use this sclerotic scatter. So sclerotic scatter is based on the principle of total internal reflection. Another application of total internal reflection is the mirage phenomenon. So the mirage phenomenon, meaning that we can see reflection of objects in the ground that is not real. It's a mirage. So how do these objects form? This is by the principle of total internal reflection. This occurs in the hot weather. So in case of hot weather, you can see that the hot air is adjacent to the sand. This, for example, this is a desert, and this is the sand. So the hot air is more toward the earth. So that is more hot, Then as we go outside or go up, then the air become more cold. So as we go to the more cold air, the refractive index will increase. So what happens if we see this image of the tree? The image of tree will pass from higher refractive index to lower refractive index. So from higher dense to lower dense, higher dense to lower dense, until a specific interface whether when the light rays passing from or reflected from the cornea, so sorry, from this tree, will undergo total internal reflection. So it will now pass through the eyes of the person, and this person now can see the image of this tree in the ground or in the desert as an inverted image. So this is based on the principle of total internal reflection. So this total internal reflection can make us see sheets of water on the ground as we're driving. This is because as I told you, that the air, this is just the reflection of the image of the sky. So as light rays coming from the sky, it will pass from areas of higher refractive index to areas of lower refractive index until it undergoes total internal reflection from here, leading to visualization of this sheet of water on the ground, which is just simply reflection of image of the sky. Finally, finally we will talk about the dispersion. So the dispersion is the breakdown of the white light into its constituent color. So if we have white light that is enter into a prism like here, which can cause one of the properties of the prism that can cause dispersion of light, this will lead to separation or dispersion of the light into the spectrum colors, as you can see here. So again, white color, when it is entered into the prism, it will lead to dispersion of the components of this white light, which are the breakdown of the white light into the spectrum of colors. Please note that this is an application of refraction, because when the light rays are this light enter the prism, it will undergo both refraction and dispersion, and this dispersion or this refraction will be different according to the wavelength of the light. So if we say that this is we have here the visible light spectrum from the red light having larger wavelength to the blue spectrum, which has a smaller wavelength. The smaller wavelength of light are bend more than the longer. So here we have the light here with the white light. The blue light is bend more than the red light. This is because this is one of the factors that control refraction. As we said, that the more the wavelength, the less refraction. The less the wavelength, the more refraction. So the blue light tend to bend and tend to be refracted more than the red light. So what is the application? Why we do see a rainbow? This is because the sunlight, after a rainy day, the sunlight will enter inside the water droplet. So it undergoes refraction, and it will undergo also dispersion. So it enters within the water droplet and it undergoes total internal reflection, and when it emerges from the water droplet, it will disperse or cause dispersion into the spectrum of color from the red to the violet. So the violet or the blue spectrum will deviate more than the red. So if we are now after sunny days, after rainy day and the sunny day, the sun will cause the light rays will enter inside the water droplet, cause dispersion of light, and by group of dispersion of different water droplets, this what will make the rainbow. So thank you very much for your attention. Now we will finish the first lecture. We will take a break, and then we will discuss the second lecture. So if you have a question in the refraction, please tell me in the chat box. Any question? So no answer, meaning that everybody understand everything? Okay, you're welcome. So we'll just be back in 10 minutes to discuss the prisms. So prisms need to be very alert because it is a little tough and has a lot of clinical applications.